Today we're going to talk about nuclear instability. You probably think of an atomic bomb when you talk about nuclear instability, but there's a lot of other sources of instability. The way that we determine if something is considered stable is by taking a look at the nucleus. We look at the neutron to proton ratio. So we have two groups. We have light nuclei and heavy nuclei. So for light nuclei, that goes from up to atomic number of 20, which is calcium. So calcium and under, the neutron to proton ratio should be 1.1. So if we take a look, common isotope, let's look at sodium. There's sodium 23 and sodium 24. So again, that number is the mass number, so we have to figure out the number of neutrons and the number of protons. Since it's the same element, it's going to have the same number of protons for both of them. It is 11. For neutrons, we have to subtract that, so we would have 12 in sodium 23 and 13 in sodium 24. The next step is to take the number and divide both sides by the number of protons, which in this case we're dividing everything by 11. So that gives us a 1 for the number of protons. So for sodium 23 it is 1.09 and sodium 24 1.18. So often with this stability, you're comparing the various isotopes. So in this case, sodium 23 is going to be more stable because that number is closer to 1. Now in this example, the numbers happen to be above 1. They can also be below 1 as well. It just depends on the isotope. For heavy nuclei, 20 and above, the ratio of neutrons to protons should be 1.5 to 1. So they're bigger, they have a larger surface area, so it requires more neutrons in order to stabilize the atom. So let's take a look at copper. We have copper 63 and copper 64. So if we were comparing these two, copper has an atomic number of 27, so it has 27 protons in both. Copper 63, we would take 63 minus 27, which gives us 36, and then this one would be 37. So we're going to do exactly the same thing. We're going to divide all the numbers by 27, so we'll have 1 and 1 for our number of protons. So 36 divided by 27 gives us 1.33, and 37 divided by 27 gives us 1.37. So in this case, copper 64 would be the more stable isotope because it's closer to 1.5. So again, you're usually comparing these values. You can compare different isotopes of different elements. However, usually it's the same element in just different common isotopes. So in this case, copper 64 is, of the two, is more stable. So all you would have to do is cite the ratio of either 1.1 or 1 to 1 for light nuclei, or 1.5 to 1 for heavy nuclei. Okay. So either we have too many neutrons or too many protons. On this graph, we have that blue line, which represents the stable isotopes. So depending upon how many protons and neutrons you have, determines if it's on that band of stability or if you have too many protons or too many neutrons. So if they're above the line, they end up having too many neutrons. If they're below the line, they have too many protons. So we're going to take a look at 4 different ways of radioactive decay to help us to determine how to make a stable atom. So the first type is a beta decay. So beta is the Greek letter for B. It is a little bit different than a B. I draw it as a line and then the number 3. So this is the same as nuclear notation. So it has a 0 mass and a -1. So the difference here is that this is has a -1. So you kind of want to think of this as a electron. Now, what's happening in most of these types of decay, so for beta decay, is that this beta particle is coming out of the nucleus. So where is this beta coming from? Well, if you think of a neutron neutrons, which have quarks. Some of the quarks have a positive charge, some of the quarks have a negative charge, some of them have no charge. So if this beta particle is essentially a quark that is separating from a neutron, which is going to then turn into a proton. So that's indicating kind of what's happening here. You can see it written either as a beta particle or as this, but we don't ever say this is an electron. We always call it a beta particle. So we would do this. We would write carbon 14. 14 is the mass number of this specific isotope. It has an atomic number of 6. So because it's coming out of the nucleus, we're going to write the beta particle as a product. Now, for our purposes, you're always going to be told the type of decay that's happening. You're not going to have to determine it. But you would have to remember that a beta particle is, this component here. So on the top, we're going to have a 14. So the arrow you want to think of as an equal sign. So 0 plus what is equal to 14 in this example, so we want 14. Same thing with the bottom or the atomic number. So -1 plus what is equal to 6, so we want 7. So because our atomic number is changing, we no longer have carbon, but we have nitrogen. So this whole equation ends up being the answer. Sometimes you have multiple choice questions that asks you for a specific part, like what is the product that is produced, or what is the mass number of the product that is produced, or what is the element. So writing out the equation is a good way to get started with that if it is that sort of question. So beta particle, this is one of the more common radioactive decays. It is very small, so it can happen in almost any element. The next one is kind of the opposite in that it's a very large particle. It's called an alpha decay. Alpha is the Greek letter for A. I draw it kind of like a fish. So it has a mass of 4 and a atomic number of 2. What's this is actually, you can think of it as the nucleus to a helium atom. So sometimes it's also written like a helium atom. Now what makes this different is that there's no electrons, it's just the nucleus. And again, it's doing the same thing as in the last one. This particle is coming out of the nucleus. Usually this happens in larger atoms, usually ones that have more than 83 protons. Because if it's a small particle, it's going to be hard for it to lose such a significant component. So we have the alpha decay of polonium 210. Polonium is PO 210. Its atomic number is 84. So again, we have the arrow with the alpha particle 42. So we have to figure out what's happening with the remaining. So we need the top number, which is going to be 206, and the bottom number, which is going to be 82. So we look on our periodic table to find out what is the element that is 82. So it's lead, which is Pb. A lot of isotopes become lead or bismuth because those are the two biggest stable elements on the periodic table. Beyond that, there are not most of the elements that are there are very unstable. So quite often they will have radioactive decay occurring. The interesting thing too about the alpha particle is that it's actually able to be stopped by a piece of paper. Because it's so big, it doesn't take a lot for it to be stopped. The problem becomes if it gets, for humans at least, is that if it gets stuck in your lungs, if it's in your lungs, it's very difficult for it to get out. So then, if you've ever heard of radon in a basement, that produces alpha particles, which is what makes it so dangerous. So the alpha and beta are the two most common types of radioactive decay. The next one, this one is not very common, but it still occurs. So it's referred to as a positron. So just like before where we had the neutron breaking up into a proton and a beta particle, this one's kind of the opposite. So in this case, we have a proton, it's breaking up into a neutron and then this positron. So a positron is essentially a quark that has a positive charge. Or it has no mass and has a charge of +1. So we still write it with the symbol E because it's very similar to an electron. The only difference is that it does, again, have that +1 charge. We couldn't use P because P is often used for a proton. What this will do is that it will decrease the number of protons. So the positron emission of carbon-11, so again, this is acting, it's coming out of the nucleus, so we write it as a product in our reaction. So we have 0, +1. I always write the +1 to make sure that it's clear that it is a positron and not an electron, that you forgot to write the negative sign. And we're doing the same thing. So what will happen, the mass will stay the same. The atomic number is going to change to 5, because 1 + 5 is 6. So in this case, this example, it's going from carbon to boron. Boron has that atomic number of 5, which becomes much more stable compared to carbon-11. In the next example, we have an electron capture. This is kind of the opposite. So in all the other examples, we had things coming out of the nucleus. In this example, the electron falls from the electron cloud into the nucleus. So instead of writing our electron as a product, we're going to write it as a reactant. So this also decreases the number of protons. This is something that happens in order to decrease the number of protons. And it depends on what the charge of the nucleus is. And there's also an element of chance here. So we have aluminum 26, which has an atomic number of 13. So that's going to, oops, I got ahead of myself there. So we're going to have an electron that falls from the electron cloud. So it's just a regular old electron. And what that will do is it's going to change the identity. So we'll have 26 as a mass number. The mass number is not changing. However, now we'll have 12 as our atomic number, so it changes from aluminum to magnesium. Now, quite likely, this magnesium isotope is going to then decompose into another radioactive decay because it's still not stable before it continues. The last type of radioactive decay is gamma. Gamma radiation you can kind of think of as energy that's holding the nucleus together. So gamma radiation is just a release of some of that energy, and this occurs along with other types of decay. It does not occur on its own. So I kind of write it as an upside down ribbon, or you can kind of write it as a Y with a loop on the bottom, but it is again another Greek letter of the day. We usually don't include these in decay equations, but assume them to be released with all forms of decay. So then here's a nice little summary table. So again, for alpha and beta, there's two ways to write them. They are usually referred to as alpha or beta decay. And then positron emission, we want this to have a positive sign out in front. And then this helps to describe what's happening in terms of changes.